crawling around, searching for higher ground. Can't see in front of me, my enemies. I've tried every possibility, ability to know if I can bleed. If that's what you wanted, you won't get it tonight. 'Cause I can fly, I can fly, I can fly, I can fly. I'm crawling around, searching for higher ground. Can't see in front of me, my enemies. I've tried every possibility, ability to know if I can bleed. If that's what you wanted, you won't get it tonight. 'Cause I can fly, I can fly, I can fly, I can fly.
Because
Okay.
yeah, and look at this screen, not at this one.
Okay.
Lights are bright, so look low.
Okay.
You're going to have 15 minutes. I'm going to show a card when there's 5 minutes to the end,
Okay.
and then stop talking, and then you're going to have 2 minutes for answers, question and answers.
Question and answer.
Right, and some of the questions will come online from the screen.
Okay.
Okay?
Okay.
Right. So
Here
no, you sit there.
Okay.
It's better this way. Should I start with clock? Okay, welcome everybody to the session organized by Optimal Structural Design Committee. I'm Arek Mazur.
Optimal design is as good as the problem formulation it's based on. We can do optimization with various functions, various objectives. If we don't choose meaningful objectives and realistic and meaningful objectives, the designs will not be as good. So in this case, we should look at the objectives, the constraints, the physical models. We want to account for all important physical phenomena, the hazard representation, analysis, etc. Another thing is that we would like to have clear and meaningful outcomes to decision makers, and these may not always be engineers. And we would like to do all that within a computationally efficient framework. We don't want to wait for months for the results to come. So, to date, a huge step forward has been presented with respect to the optimal design of dampers. And to the most case, what we did is we minimized the cost of the dampers while constraining some engineering demand parameters of the buildings, such as interstory drifts and accelerations, etc. And lately we've started looking at, these are very good, and they are very viable also today, but in some cases, people that make the decisions on the scheme of retrofitting and what the goals are not engineers, and they don't understand engineering demand parameters. So it may be beneficial to look also at functions that they understand and would help them make the decisions. And there have been some steps in this direction, one of them by Puthan Purail, myself, and Dakal, and actually here we extend that. Another issue is that mostly single objective optimization has been used, and it doesn't give the whole picture to the decision maker. So this is something that I'll touch upon later on. So there is a need for decision-making supporting approaches for such problems. And the way we did that is actually, we looked at the realistic retrofitting cost, then, on the other hand, a decision-making meaningful performance measure, and we cast all that into a multi-objective framework. So in terms of the initial cost, this is still work in progress. This is the simplest cost function that we found, but we intend to actually modify it. What it takes is the sum of the square root of the damping coefficient of all dampers, and it has been shown to, under some circumstances, be proportional to the cost of the dampers. So we would like a problem that is based on financial measures. The cost of intervention or initial cost of the dampers is already in terms of money. And then how can we have a performance measure in terms of money? And one of the approaches to do that is using the expected losses. I will not go into the details, but essentially the expected losses are the losses that are expected during the lifetime of the building, in this case due to earthquakes. So it's comprised of the probability that the structure would not collapse times the expected losses, assuming the structure does not collapse, plus the probability of collapse, P of C, times the total building value. And the expected losses, again, if the building does not collapse, I don't want to get too much into details, but we'll see it in this slide. The computation of that is comprised of 4 stages. It's based on the peer framework, and we take into account uncertainty in the hazard, then uncertainty in the structural response to the hazard for a given hazard level, then assuming the structure responses in a certain way, and we have certain engineering demand parameters, we take into account the uncertainty with respect to the probability of exceeding a given damage state, and then this is also translated to losses. And one thing to bear in mind is that each function evaluation here is very, very computationally expensive. In the structural analysis cube, we have many, many nonlinear time history analysis. So since the function evaluation is so expensive, we would like the optimization approach to be very efficient and reduce the number of function evaluations. Now, we looked at the initial cost, we looked at the expected losses. Why multi-objective optimization? Well, if we look at this objective space, where we have the initial cost on the vertical axis and expected loss on the horizontal axis, for each design, for example, CD1 and CD2 here, we can evaluate the initial cost, we can evaluate the expected losses, and we have a point on this space. So, for example, in order to solve an optimization problem, a single objective optimization problem, the engineer could actually limit the expected losses or constrain them to allowable values and minimize the initial cost. And he would get an optimized solution. He would probably get a medal from the client. His boss will not be happy for him wasting time on optimization. But the question is this really an optimal or an optimized design? And the answer is yes. For the problem that the engineer solved, this is an optimized design. But what would have happened if the engineer was willing to compromise a little bit on the expected losses and re-optimized the structure? In this case, he would get a new optimal design, and it could be that with a small compromise in the expected loss, he would get a much smaller initial cost. And he doesn't see that because some parameters like the allowable expected loss were set a priori. And here Pareto comes to the rescue. So if we look at all the feasible solutions on the design space, and we'll take a look at this specific solution, this is a Pareto optimal solution, since there is no other solution that would reduce one objective without increasing the other, meaning there is no other solution in this shaded quadrant. And the set of Pareto optimal solutions, there is no one optimal solution, but a set of them, is called the Pareto front or the Pareto set. And when the decision maker has this at hand, he has the whole picture at hand, he can make the best compromise without setting any parameters a priori. So this is a very good tool for decision makers, but it usually involves a very large computational effort. So again, our approach tries to minimize this computational effort so that we could obtain this Pareto front in a reasonable time. So our approach, essentially, we adopted a gradient-based multi-objective optimization approach that was proposed by Izui et al. In 2014. And for the complex functions that we have, we actually use the adjoint analytical method to derive the gradients necessary. And it resulted in a very, very efficient approach for this specific problem. So let's take a look at some results. Here we can see a 5-story, 3-bay frame that we wish to retrofit with viscous dampers. We allow dampers to be mounted on the central bay, one in each story or a few in each story. The exponent was taken as 0.35 and the maximum damping coefficient as 1,000 with the appropriate units. And we ran the optimization and we got this Pareto front, and we will take a look at 6 different points on this Pareto front. So the first point, we can see that there is no initial cost, meaning we didn't put any dampers, and there's a relatively large expected loss. So on the figures on the right, you can see the damping distribution along the height, 0 damping in this case, and the loss per story. And we can also see the probability of collapse that is relatively high. On the figure below, we can see that for the second point, we have a large damper on the 3rd story, and the loss per story is substantially smaller. Note in these figures and in the next figures that the damping distribution between the different points on the Pareto front are very different one from the other. So We can see here point 3 and point 4. Note that in point 4, actually, a larger damper was put on the second floor rather than on the fourth floor or third floor as before. And we have here points number 5 and 6. So to conclude, we believe that we formulated a meaningful and very good optimization problem for decision makers, because we use multi-objective optimization with functions that decision makers that may not be engineers well understand, and they can make the decisions based on those. And behind this Pareto front, there are actual designs for the dampers. And we did it within a computationally efficient approach. One more thing, I would like to acknowledge the Israeli Ministry of Science and Construction for funding this research through the National Building Research Institute. That's it. Thank you very much.
Thank you for having me here. And I hope you enjoy it. This is a No, this is not my presentation. This is Ed De Paulo. Would you want to step up?
Can we please change to the optimal design and reinforced concrete structures, please? Okay.
This is my presentation. Eugene Kim, that is here, was the associate partner in charge of this project that I'm going to showcase, and Nicolas Gomez was an engineer that helped. We heard a lot about that the important thing is to know what we want to optimize, and I couldn't agree more. And we're going to talk about the criteria in building design, and then we'll do a case study. What is optimization? We all have an intuitive knowledge of what is optimization, and we all have an intuitive knowledge of what is an optimality criteria. It's the criteria where we judge if we had optimized or not optimized. In construction, there is 3 basic stakeholders: the owner, the contractor, and the design team. And further, the design team is composed for a number of people: the architect, the mechanical engineer, the foundation engineer, and the structural engineer. And we have nothing in common. The only thing we have in common is we want to get the project built. We want to make it safe, and hopefully we want to make it sustainable. And then the rest, we're all on our own, and we have a different objective. The owner is money, the contractor wants to be familiar with what they built, the architect has to meet the program, and the structural engineer generally is focused on economy. And this is not new. This has been around forever. This dichotomy in architecture comes from before Christ. How do we optimize the structure? Well, we can, as structural engineers, I think that the most important thing is to select the structural system and the material. Once you know what material you want to work in and what is the structural system, you have to work on the different layouts that have a number of components. Then you find what is the material strength, and at the end, we work on the member sizing. In this case study that I'm going to show you had 3 different buildings. It had a townhouse component, it had a parking component, and had a residential component that was a rental. The owner and the contractor and the the owner representative were very experienced. They had done this several times before. And they knew that for the townhouses, the best system for them was the Hambro. For the parking, the precast garage. And for the residential tower was the concrete flat plate. And they knew it because they had the numbers on their return of the investment. So there were 3 different buildings put together on one site, and the massing was something like this. So it was nearly a city block, 200 by 200, and this was going to be 480 foot tall. That's to the last floor, not to the top of the roof. So it's very short floor to floor heights. It's a big project, 670,000 square feet. This was the most important decision. And this took months. The decision to make all the project in one material only, to make it all in concrete, to have a SAP that will work in concrete, that you will give him a huge contract so he could give a better price, that the site could have better logistics, that there will be less mobilization, and there will be fewer contractors. This was the hard decision. The team did not start here. So we did it with one building. We did it without joints. We had to put fire separation. And we did it with one structure. Just by joining the structures, we saved on the lateral system of the lower buildings. The lower buildings can be supported by the taller building, or if we want to put a lot of structure on the lower buildings, they can actually act like as an outrigger or as a point support for the bigger structure. The next decision is, where do we put the structure? Do we put it on the outside of the tower, or do we put it on the inside of the tower? And the external system was rejected. It didn't go with the owner's vision. It was unfamiliar for the contractor and impacted the architecture of the apartments. This would have been a very efficient structural system. So now we go to the wall location. So we had a shear wall system. What you see there is that the walls are around the elevators and around the stairs. We want the walls around the stairs in case there is something happens that the stair is protected. What is in black is the trash chute. Typically, we want walls around the trash chute, but in this case, the noise of the trash chute was far away from the bedrooms, so it was not really relevant. Talking to the team, what was the concerns of the team? The concern of the team, of the contractor, was the link beams. They didn't have a good experience with link beams. They wanted floor plates that were open and accessible to finish the job. The architect wanted as much space as possible for the apartments. And they definitely didn't want noise, and the contractor didn't want to change sizes every 2 floors. We decided not to put the conduit in the slab. This was a decision of the team. The conduit was put under the slab. This is an example of a link beam of another project. The link beams delays the construction and creates a lot of coordination problems. What you see on your right is an actual slide of another project, and that's what happened after the coordination, the mechanical coordination was done. So the link beams many times get very hurt in the process. So there was a decision that there was going to be no link beams. Another hit on the structure. This makes the structure more expensive, but the team thought that this was an excellent decision. What you see in blue would be the optimal wall placement if we had on the up and down direction of the slide to get some stiffness, right? But as you can see, the optimal wall placement didn't match the architectural layout. The architectural layout, as is a rental building, is again based on a return on investment. So these were all the possible locations of the walls. In the end, this was the location that was picked. And you can see it's a little bit eccentric, but it has no impact on the architecture. The contractor, and what you see there is the hoist, did not want this. They did not want to have all the flow of all the material for the site to go through the center corridor. What they wanted is this. So we designed this. In other words, we put holes, staggered holes on the shear walls, so you wouldn't need link beams to give the contractor access to the floor. The owner was not familiar with this approach. The owner realized that he was not getting a break price in the concrete, and the owner realized that he had to pay more to the finisher because now he had to fill in a number of fire-rated walls. So this was rejected. When you do one of these buildings, what you want to do is increase the tributary area of the core as much as possible because you have a lot of concrete on the core, and then you reduce also the uplift. So we moved all the columns away from the core. And you can see on your right that some of the columns we made them longer to keep on with an 8-inch slab. So this was the end, the tributary area for the core. As you go down, you have a center of rigidity because now suddenly you are engaging a little bit more mass. So that would be the structure, and you can see this is very asymmetrical. Hence, we put a wall there that is the other fire separation. The floor-to-floor height of the townhouses is different than the parking, right? And you can see again that we're encasing the stairs and the elevators and helping on the accommodation of the diaphragms when you have the diaphragm doesn't flow from one building to the other. Finally, we come up to what we really want to do, that is control the drift and the period. In lower buildings, we have to satisfy the drift. In taller buildings, what is important is the period, because the period gives you the forces. So this building had a wind tunnel test, and we were trying to optimize the period to reduce the forces. So what Bill Lemesher saw many years ago is that a structure is optimal whenever you have the structure and you move it around, it contributes to the deflection the same amount. The way to do this is through the principle of virtual works. You have two independent sets of forces and displacements in a building, you compute them, and if the force of one and the displacement of the other equals to the internal energy of all the other members, this is very easy to do computationally, and this is the method we use. In addition, for taller buildings, a disciple of Bill Lemesher, Richard Henning, found that you can also use the virtual work to optimize for the period when the two sets of forces are the inertial forces. So we did the member sizing. We did it with ETAPS. ETAPS has a routine that asks you for what is the relative strain energy of all the members, so you can go there, and then you can pick and select the members. Here in the contractor and in attention to the spans, we made all the slabs 8 inches, all the slabs were 8,000 PSI. The shear walls were 10 KSI, the rest up to the 22nd floor, and the rest were 8 KSI. We could have gone to 14 and 16, but again, the contractor said, stick to 10, because I know that I can get that no problem. So that's what we did. This project took 7 months to build. We did a 2-day cycle. This is 2.5 floors a week for 38 floors. And the bottom floors that are 40,000 square feet take approximately a week. You cannot pour more than 20,000 square foot a day, every 2 days, at least in our experience. So the minimum of the superstructure would be 6 months. This took 7 months, including that we were through winter and through the holidays. And there you have it. You see in the right that the townhouses came first. That was a good decision. We asked for an external system. We were forced to have an internal system. This was not good for the structure. We asked for link beams. We didn't have link beams. We asked for the walls of the shear walls to be aligned so they can work. We didn't get that. We got offset walls. The contractor asked for holes. They didn't get that. They got a single hallway. And finally, we did the column placement and the member sizing. You can see that you have to compromise where you do optimization. It's a team. And what is good for you may not be good for the others. Listen to the stakeholders. If you remember something about this presentation, this is the most important thing. Thank you.
You all learned it either in sophomore or junior year of college. It is relatively straightforward. You have a real force system and a virtual force system. The way it works is that the deformation is the sum of the P times delta L, where P is axial force, and the M bars times the change in the rotations, with those being PL over AE and ML over EI. And you see the bottom equation, number 1, it is simply, if you use a virtual force of 1, that your deformation is the sum of the PP bar L over AE, and if you have moments, you include MML over EI, and if you have shears, you can include those, and if you have three-dimensional, you can include MX and MY. You can include as many as you want as long as you take care of them. What I'm going to show you today, because of the limited time, is very simple. It's a braced frame. So you have to assume that, or it could be used for a truss, I'm sorry, but for today, a braced frame. And you have to assume that all the other optimizations have already taken place, right? We've decided that you have bracing on these column lines in the building, and you have outriggers and belt trusses at these floors in the building. You have your geometry. I'm not trying to optimize that. The basic mathematics, like the basic engineering, is about 300 years old. You use Lagrange multipliers, simple and straightforward. I'll read this one to you because it's important. You want to minimize a function, lowercase f of xy, where x and y are subject to a constraint described by another equation. We'll call it phi of xy. And you make this equation that is capital F is equal to small f plus lambda, which is the Lagrange multiplier. You set the partial derivatives of x and y equal to 0, and you solve for the unknowns. And you're going to be pretty amazed at how simple this is. This works for any number of variables. And I'm showing you x, y, z here, but as you can imagine, in a 1,000-foot tall building, every diagonal brace, column, outrigger truss piece is a variable. There's A1 through A2000, and what you want to do is optimize them. The way we did it in the old days was we did the accounting spreadsheets. We multiplied P, P, L, and divided by E, and we looked in the column and saw which ones had the biggest number. It was the biggest contribution of drift to the total answer. So let's do this. We have small f function, which is the density times the area times the length. It's basically the volume of the element, the volume of the element. And I'm going to add them all together, as many as I have. The constraint, in this case, is the definition of a displacement at a given point. And that's the virtual force method. The sum of the PPL over AE is equal to some number. It's a constant. And when you fill them all in, you get capital F equation. And then for an optimized structure, you take the partial differentials of each of the functions in relation to each area. And what's important in the bottom, something to remember after the next slide, is that all of this, the Lagrange multipliers times the partial differentials, has to equal 1.0, or should equal 1.0. And if you fill in all the numbers, and I'm sure you can somehow get a copy of this PowerPoint. If you want to email me, I'll send it to you. You fill in all the numbers, the bottom equation 6 is it. The Lagrange multiplier times the PPL over A squared E. The A squared comes because you took a partial derivative in a step before. And that means that the Lagrange multiplier times the strain energy density of the element is equal to 1. And when that occurs in every element on the project, you have an optimal structure. Optimizing, again, volume and hence area. And I'm going to do this hand calculation. Very simple, 3-element truss. There's a 100 kip load on it. You see the dimensions. The Excel spreadsheet printout shows you the P, which is the real load, the virtual load, lowercase p, which is based on a 1 kip load, and the length of each element in inches. I plug all that information into the equation that I showed you before for capital F. I take the partial derivatives with respect to each area, one at a time, and you see what I come up with in the right-hand column there. I come up with that lambda is equal to 444 times A1 squared, 569 times A2 squared, and 888 times A3 squared. And if I set them equal to each other, which is pretty simple, basic, algebra, I know that A2 and A3 are related to A1 by those values. So now I plug them into my equation, knowing that at the end of the day, the drift I'm hoping for is 1/2 inch. And when I solve it, I get the values across the bottom. There's no need for me to read them. And now I'm going to show why those are the optimal areas. You can see this. You put that in, and you can solve for your Lagrange multiplier, which really isn't something you need except to prove this at the end. And you look at the area of each piece now. There's the optimized area. You look at the strain energy, which is PPL over AE. You look at the strain energy density, which is just divided by the volume, and you multiply the strain energy density by lambda, and you see in the right-hand column it's all 1. Everything came out to 1. And the total of the strain energy, the PPL over AE, comes out to the 1/2 inch. And now that's a small little problem that you do by hand with a pencil and a calculator, and very simple to use, right? Sometimes, most times, you come up against a constraint in element sizes. You may have a truss, for example, or a high-rise building where you can't let a column be less than some size, maybe for gravity load. And pretty much that's one of the reasons you do this. And you want to specify, I'm going to hold that, I want you to do this, but don't change the area of this one element. And so I do it again, and I say, in this case, I'm going to take A3, I'm going to hold it constant, I'm going to run the same thing. You could see it's the same forces and lengths. I'm going to do the same equation, leaving out A3, get my partial differential, and I can relate A2 to A1. I put it in the equation. You'll notice on the right-hand side, I took the 1/2 inch that I wanted, and I subtract the strain energy contribution from A3. I subtract it from the 1/2 inch, and I get that A1 and A2 values across the bottom of the screen. And you put them in this spreadsheet, and again, you'll see that the sum of the third column is 1/2 inch, and all the numbers on the optimized elements in the right-hand column are 1. Now, I showed you this in very simple terms on a statically determinate frame with axial force. As I said at the beginning, it's valid in 3D. It's valid for moments, it's valid for shears, and it's valid for all of them at the same time. The key is to be able to find a way to relate the moment of inertia to the area. And I don't have it in the presentation because of the lack of time, but you can go into the steel manual, for example, and you can plot and do a linear regression of every W size in the manual. And for W14, you can come up with an equation that relates I to A. It's pretty close. It's amazingly close. So you substitute I for A times this factor that you work out, and now you can do combined axial and moments. The last thing I'm going to show you here is that for statically indeterminate frames, because I've only shown you statically determinate, the indeterminate frames, it's exactly the same process. But because the forces in an indeterminate system are dependent on the stiffness of the system, as you change the areas around, the forces are going to change. So you necessarily have to iterate. However, you will see here that using the same method, and this is the iterations, The volume of the structure in iteration number 2 hit 186, and in iteration number 3 didn't change, which means in this, I know it's only a 3-story, 1-bay structure, but it converges very, very rapidly. And as a matter of fact, those of us who use this in our practices can tell you that if you do it once, even for a 1,000-foot tall building, you're real close to where you want to be, and there really isn't much need to go much more than that. That's it. I tried to keep it as simple and straightforward as possible, and these, as I said, you could do this with a pencil and a calculator or make a spreadsheet for yourself. So it's something that every structural engineering firm can use. Am I okay on time?
Oh, the train is going fast.
Thank you. Hello. Today I will talk about optimization-based design of nonlinear moment-resisting steel frame under seismic load. First, I want to acknowledge the Israeli Ministry of Science, Technology, and Space for the financial support in this research. So I want to open with a question. How to design? What is the best way to design a new steel moment-resisting frame subjected to seismic load with performance constraint? Using conventional design tools as force-based design or direct displacement-based design in many cases might lead to inefficient, costly design, in particular when irregular structure to be designed. A possible solution we propose for this problem is to utilize the optimization-based design approach for this task. In the literature, we can find a number of works that use optimization methods for this problem. Some utilize the static nonlinear analysis tool as the pushover analysis. Others use the heuristic optimization tools, genetic algorithm, or simulating annealing. The heuristic optimization tools are very popular in the field of structural optimization and can easily modify for a more reliable analysis tool as a nonlinear time history analysis. But on the other hand, they are very computationally demanding. Also, analysis redesign used for this problem. The analysis redesign is a very practical and easy to use analysis tool, but on the other hand, it's not a formal optimization tool. In the presented work, we will focus on the gradient-based optimization approach. The gradient-based is known as very efficient optimization tool. It is a formal optimization tool, and the response of the structure will be evaluated based on nonlinear time history analysis. The objective of this work is to develop an efficient gradient-based optimization methodology for the design of new steel moment-resisting frame subjected to earthquake with performance constraint. And the contribution of this kind of work is the proposed methodology will be able to solve an irregular, large-scale, real-scale frame with large number of design variables with reasonable computational cost. So the problem formulation for the optimization process, the objective of the optimization process is to minimize the total volume of material in the structure. In our case, it's the total volume of steel in the structure. Then we have the constraints. The first is the performance constraint, the interstory drift, where the peak interstory drift at each one of the stories is limited by a predefined allowable interstory drift. We also consider the strong column weak beam and column size criterion. The response of the structure during the earthquake is evaluated based on the solution of the nonlinear equations of motion under the load of ensemble of ground motion records. And the cross-section properties for each one of the members will be selected out of a standard, a predefined set of standard steel table where the plastic modulus W represent the cross-section properties. The solution scheme for the gradient-based optimization method is as follows. We start from initial solution, initial design. Then we evaluate the response of the structure first by a static analysis tool to consider the gravity load, and then we use also the nonlinear time history analysis. In the next stage, we evaluate also the sensitivities of the problem of the objective function and the constraint with respect to the design variables. And in the next stage, we using the sensitivities to approximate the problem to a subproblem. In this case, we utilize the sequential linear programming approximation, and then solving the optimization subproblem, and we repeat on this process until the problem converge. I will start with the nonlinear time history analysis. We have a 2D frame model under the load of deterministic ground motion. And at each beam column connection, we have a 3 degrees of freedom, one horizontal, vertical, and rotational. And the response is given by the solution of the global equations of motion. And we use the Newmark beta time stepping integration scheme. Because the nonlinearity of material, we use also the Newton-Raphson algorithm, and we also consider the P-delta effect by geometrical stiffness metrics. For each member beam or column in the model, we use this force-based element as presented by Spacone. In this case, it's a 2D Euler-Bernoulli beam element that also used by Paulini, Lavan, and Amir. We take into account the interaction between bending moment and axial force, and at each element we have number of control sections, and for each control section we use this differential equation to describe the relation between moment and curvature at each control section. After we successfully evaluate the curvature at each control section, we can evaluate the beam end rotation by using numerical integration. Now I will move forward to the sensitivity analysis. And in order to utilize an efficient gradient-based optimization solution scheme, we must first all our function, the objective function, the constraint, and also the design variables to be in continuous differentiable form. And I will start with the reformulation of the design variable, where we have this predefined set of profile and W1, W2, and so on. And below, we reformulate the plastic modulus W of each member by the vector X of continuous design variable, where each X is defined in the interval between 0 and 1 as a continuous design variable. Now we want to evaluate the gradients of the objective function and the constraint. And the objective function is an explicit term of the design variable X, and therefore we can evaluate the gradient of the objective function explicitly without any major obstacle. The constraint, the performance constraint, is much more difficult to evaluate because the peak interstory drift is given by the solution of the equations of motion, the nonlinear equations of motion during the earthquake over time, and therefore we first rewrite the original non-differentiable term constraint as one aggregated differentiable term. And then we utilize the adjoint method in order to derive the gradient of the constraint in an efficient way. So in this stage, after we successfully evaluate the gradient of the objective function and the constraint, we can use the gradient-based optimization solution scheme. But because we reformulated the plastic modulus W of each member by a continuous design variable, we cannot ensure the final design will be practical and be compatible with standard steel table. For this reason, we adopt the discrete material optimization function, DMO, and we added the parameter P, known also as the penalization power. And the concept of this DMO function can be illustrated by more simple function, the SIMP function. And at the figure, the x-axis represent the cost, the y-axis represent the plastic modulus we consider for the analysis. And in this way, for I value of P, Binary values for X are preference, and the optimization deriving forward a discrete final design that is practical and compatible with standard steel table. Now I will show two numerical examples. The first is a simple example of two-story, one-bay frame under the load of the El Centro ground record. In this problem, we have two design variables. The first is the plastic modulus of the columns, and the second, the plastic modulus of the beams. We consider the European standard steel table, IPB type for the columns, and IPE type for the beams. And the interstory drift constraint of each story is set to 1.5 of the height of the same story. Here the contour map of the problem. The x-axis is the plastic modulus of the columns, and the y-axis is the plastic modulus of the beams. The red lines are the performance constraint, represent the performance constraint, the interstory drift. The black line represent the objective function, the cost, and the blue crosses represent all the possible discrete combination to design based on IPB type for the columns and IPE type for the beams. All of this area is not feasible because the peak interstory drift is larger than the allowable interstory drift. And the optimal discrete design is IPE 300 for the beams and IPB 260 for the columns. At the left side, you can see how the plastic modulus of the columns and the beams properly converge during the iteration of the optimization process and achieve the optimal discrete design after 32 iterations. At the right side is the response of the optimal structure, the interstory drift of the first and the second stories during the earthquake, and the red lines represent the allowable interstory drift constraints. Now I will show a real design case, a 9-story setback structure, irregular structure, also under the load of the El Centro ground record. In this problem, we have 53 different design variables, 53 different types of elements in this structure. We consider the European standard steel table, and the interstory drift constraint is set to 1.5 of the height of the same story. After 171 iterations, we achieve this optimized structure. At the left side, the thickness of each line in this figure represent the cross-section properties of the same member. And at the right side, you can see the response of the optimized structure is the peak interstory drift normalized by the allowable interstory drift for each one of the 9 stories. And you can see none of the stories violated the interstory drift constraint. The red line represents the constraint. To conclude, the numerical results showed how the proposed methodology successfully solved realistic design cases, large-scale problem with large number of design variables, as the 9-story structure successfully solved, irregular moment-resisting frames, also as the 9-story, the setback structure successfully solved. And another important issue is the efficiency of this method from computational point of view, and the small number of function evaluation that required to achieve the optimized structure. Thank you.
A board of multiple journals. Jamie receives his PhD from Princeton University and bachelor from University of Pennsylvania. Welcome.
Thanks, Eric, for the introduction and also for organizing this session. So I'd like to talk. You're hearing a constant theme today, actually. You get what the optimization results are dependent on the problem formulation. Right? So I'd like to talk today a little bit about some things we're doing to get more practical considerations into the optimization formulation, specifically related to constructability, as well as some strength and stability type constraints. Let me acknowledge my co-authors here. So Serendipco, this work is based on them, of course. Serendipco was a PhD student, finished about a year ago. She's now at SOM, as well as Meitu Nguyenue, who's a PhD student and finishing up shortly. So we haven't heard a talk exactly about topology optimization today, so let me just give a little bit of an introduction. So topology optimization is really about finding the optimal connectivity of a structure. Okay, so not only are we trying to optimize cross-sectional areas, but also the connectivity of those cross-sectional areas. And as in typical topology optimization formulations or optimization formulations, we have an objective function. Often that is something like minimize mass, right? As well as constraints, which always includes equilibrium, okay, and often will include some performance constraints like a deflection constraint or some stiffness metrics or something else. And then that bottom line there you see is bounds, right? We have minimum cross-sectional areas and maximum cross-sectional areas. And for truss topology optimization, we often take what's called a ground structure approach, right? So if you look at the bottom left there, you see a very complex structure. You see boundary conditions and loads. And that very complex structure called the ground structure is basically all the possible combinations of members, right? So every possible candidate location a member can exist, as well as the connectivity of those members. And it's the topology optimizer's job to whittle those away, right? So optimize the cross-sectional areas. Areas that go to 0 should be removed from that ground structure, and then you end up with that structure there shown on the right. All right, so this is a really nice approach, has great advantages. It creates highly efficient structural solutions. It's very systematic. We start with that ground structure. We have to create that ground structure. We have to create a problem formulation, but then ideally we hit go, and a gradient-based optimization solves the problem for us, right? So those are very nice things. But as we've heard today, it will only optimize what you tell it to optimize, right? So if we do not consider constructability, we can get complex structures like this. So this may be highly efficient design, but really costly or impractical to manufacture or erect. And also we haven't talked about stress or buckling in that problem formulation, and so we can't guarantee that those will be respected. And I'll come back to that towards the end of the talk, how we're going to address that. So let me talk a little bit about how we're thinking about constructability. We've done quite a bit of work in manufacturability and continuum topology optimization, where you have actually solid elements and trying to arrange those in ways that make things easier to fabricate. And we're trying to bring in some of those ideas now to truss and frame structures. So 3 things that we've looked at in terms of constructability, and these are really first cuts, and we'll show them on very simple illustrations to show how they impact the optimal design. The first one is complexity. Right, so if we look at that beam in the upper right there, the one on the left is very simple, but also very inefficient. And the one on the right is very efficient, about half the mass of that other beam, but much more complicated. Right, so we need a tool that helps us navigate that space, navigate those trade-offs, and create design alternatives that balance structural efficiency with complexity of the design. Another one we've looked at is repeatability, right? Custom member sizes. So obviously we can't pick any cross-section. Maybe it has to be custom made. That comes at a pretty large premium, cost premium. Oversized members may come at a cost premium, right? And if you look at our structure here, we have very, very large members near the root of that beam, and maybe those incur cost premium. So can we actually drive the optimizer to choose more standard section sizes or avoid things like oversized cross-sectional members? And the last one there is repeatability, right? That truss actually, almost every cross-sectional area is different, right? So every member has a different section size. It's symmetric, so we're talking about half of the structure here. But almost every member is different, right? And that's obviously very undesirable. It's very complex, not only in the acquisition of those members, right? Maybe we can get volume discounts if they're all the same size, but also just managing the assembly of all those different beams, right? So can we encourage the optimizer to repeat cross-sections? And our goal here is to create plots like this, right? So as we sort of implement these constructability constraints, can we see the trade-off between structural efficiency and things like complexity, right? As we ramp down complexity, as we restrain our optimization, obviously we're going to get more inefficient structures, right? And the goal is, can we provide design alternatives and allow the designer to make a decision then weighing those 2 things. So 2 things I want to say here is, first, we want these things to be physically meaningful, right? We'd love actually to have a real cost number associated with these things. That's kind of difficult. It's kind of a fuzzy number. So often our goal is really not to identify a single solution, but rather, again, this trade-off space. Two, the real challenge here is trying to estimate these things in a continuous manner with continuous functions. Okay, so everything I'm going to show you has been using gradient-based optimization, so the design variables are continuous, and the functions to compute these things have to be continuous. Right, so part of this work is finding creative ways to express these metrics, right, so that they work in a gradient optimization setting. So I'm going to start with very simple ideas and very simple structures just to illustrate the impact of these things. So the first thing we'll look at is complexity. So if we take our objective function and we want to minimize material costs, we now add a complexity cost to that. Right? And that complexity can be expressed many different ways. The simplest is shown here. That alpha is maybe a cost per member installation, a cost per connection, and that H function there is really a heaviside function to count how many members or how many connections exist. Right? So the challenges here is, remember, we had that very complex ground structure. As areas go to 0, they no longer have to be constructed, right? So they drop out. So this H term here will count the ones that are remaining in the structure. Anything above 0 will count as one element existing. And there's lots of permutations of this. Again, we can do it per member, we can do it per connection. We can have the cost be a function of the members at a connection. But they'll all use the same kind of fundamental math here. So when we do that, we see things like this, right? So if we look at the structure on the bottom left, you have a highly complex structure with no penalization for complexity, no cost for complexity. As we ramp up that cost of complexity, the structure gets simpler, right? And all the way to the far right, the simplest of the structures is a 2-bar truss. Now, of course, as we do that, the structures lose efficiency, right? So if we look at our plot there, as we move to the right, the material cost or the material volume is going up, and the complexity is going down. Right? And as an engineer, you might look at that plot and say, well, my complexity is going down rapidly, that's good. My material volume is pretty constant. It's increasing always, but it's a small increase until I get to that 2-bar solution where I see a massive jump. Right? So maybe I would want to end up with that second solution from the right, because if I take one more step, my material cost skyrockets. Right? So again, just trying to provide a tool to navigate that space of complexity and structural efficiency or material volume. Another problem we've looked at is repeatability, encouraging the optimizer to have sections that repeat. And here it's really just, again, sort of economies of scale or volume discounts. This is a very simple table of the more I buy, the cheaper the members are, right? So if we express that table as a plot, and then we try to express that in our optimization formulation, here we're basically just changing the way we could compute material cost. So RA is kind of adjusted cost now. This calculation is somewhat complicated, so I'm not going to go through every term, but basically the idea is very simple. When I have a given area, I see how many members have a similar area. That tells me the discount, right? And then I can sum those up and go to the next element with a different area. Okay, the key is it's a continuous function. It's a function of my input discount curve, right? And then the optimizer will work on that. And when I do something like that, you see things like this. Okay, so this is just considering repeatability and discount curves. If we don't have any discount for repeatability, we get that structure I've already shown on the top. Okay, and then as we encourage repeatability with discount curves, you see more members being added and you see less variation in the line thicknesses. Right, the number of members with different cross sections is going down, and that's shown on that plot on the right. Okay, so that bottom curve is the number of different cross sections normalized against the original number. And of course, as we do that, we lose efficiency. Okay, again, as we require the optimizer to repeat section sizes, we're going to lose structural efficiency and have more material cost. So that top curve is moving up as we do this. Now, in the extreme, if we have major discounts for buying lots of stuff, you end up with a structure that uses all the same section size, right? That very complicated one on the bottom. Obviously, we would want to take our previous complexity constraint and add it to this to balance both of those things. So one thing I'd like to say here is we're not imposing repeatability. We're not forcing the optimizer to use repeatable members. That would be much easier as a constraint. Rather, we're giving some cost, right? Some cost benefit to doing it and letting the optimizer navigate whether it's worth it to have those repeatable sections. And then one other example is the one on the right. I sort of trimmed down what I was going to show, but the one on the right is another example of custom sizes, right? So if we want to use non-standard sizes or really large structural section sizes, oversized members, for example, we can turn on cost premiums when those cross-sectional areas hit those values, right? So just that top curve there is just an example of a cost premium kicking on when our area reaches a certain value. And the picture there on the bottom left is a very simple, on the bottom right, is a very simple truss. And if we're allowed to use whatever cross-section we want, we get a large 3-bar truss, a 3-bar truss with large members. And at some point, if those large members become too expensive, you see it design a redundant structure with smaller members. Okay, so again, trading off complexity, or in this case, custom sizes for material efficiency. So those are some of the constructability things we've looked at. Now, in terms of other constraints, like, of course, stress or buckling or global stability constraints, if we don't consider them in the optimization problem formulation, the optimizer is going to take advantage of it, right? So some of the examples I've shown you already, you'll see very thin bars on compression paths, okay? If we solve different problems like the one on the bottom right, topology optimization will actually design you an unstable structure, right? As an engineer, we see that's a problem, but because it's not included in the optimization formulation, it doesn't know it, right? And this is fundamentally because we're using a ground structure approach, right? We have very, very tiny members sort of stabilizing that system, but in reality, it's not actually going to be stable when we remove them, right? So the key is how do we get these metrics, again, in the problem formulation? This turns out to be surprisingly challenging, right? We're very good at having a very, if we have a structural design, we can predict very easily whether we violated stress constraints or predict global stability. That's straightforward, right? But it actually, in a design setting, when you're solving that inverse problem, when I change areas, how do my stability limits change? That's actually quite challenging. And this illustration on the right is just a very simple example as to why that is. So if we consider that structure on the bottom left and that plot on the right, those axes are the cross-sectional areas of that very simple truss. The blue region is our feasible space. That's any combination of areas that will satisfy our, in this case, stress constraints. And the optimal solution is actually that red point, right? So that red point is actually that 2 of the members are going to vanish. They don't exist. The areas are 0, right? And you can see as you try to navigate through that blue space, we're going to hit that wall, which is a local minimum, right? So depending on where we start in that blue space, we can't actually find that red dot unless we take a very strategic path to the A2 is equal to 0 and then move over, right? So very simply in topology optimization, because members can vanish as they approach 0, stability issues or stress issues start to spike, right? And the optimizer thinks it can't keep going because it's detected some issue, right? It's hard to get it to actually equal 0. And in reality, they're going to be removed, so they don't matter, right? So that's the real challenge mathematically with these constraints. So we've lost all of our equations. That's awesome. So we discovered this paper by Stolp and Svanberg actually many years ago called a disaggregated formulation. And the idea really simply is instead of using cross-sectional areas as your independent design variables, which has this issue as I vanish, constraints start to blow up, rather have cross-sectional areas as well as a structural response, displacements, forces, actually also be independent optimization variables. And now rather than solving an explicit KD is equal to F style problem, the optimizer actually has to solve it for you, right? It's all now solved inside the optimization. And D and F and A can move simultaneously, right? So A and F can go to 0 together, and you don't get a stress and spike that way. Okay? The other nice thing about this is the gradients are trivial, right? So you can't see the equations, but they're all linear expressions in those variables, one nonlinear expression. So they're very easy to compute the sensitivities for gradient-based optimization. And this example has yielding constraints and local buckling constraints as well as global stability constraints. And when we do this, we get solutions like this, right? So the top right one is our original solution I've been showing you. And when we do this approach with all of these constraints considered, including global stability, we end up with a structure like the bottom right, which makes more sense to us. It's no longer symmetric. The compression paths are larger than the tension paths, right? All sort of feel better as a structural solution when you start to think about buckling and stability and things like that. So I'll wrap up there and just like to conclude that topology optimization is a really nice tool for finding new structural solutions. But the catch is you have to have things you care about in the formulation, right? The idea of optimizing and then cleaning up and imposing your sort of biases after the design process can actually lead to very bad solutions. We'd like to get those things actually in the optimization formulation. whether things like constructability or things like, of course, strength stability constraints or behavior post-elastic regime. Of course, these things all have to be bundled together, right? They all have to be going on simultaneously. That's our goal. Fortunately, we didn't get it done in time to show you today, but the goal is to have them all working together so that we can solve these problems with all of these things active. And I'll stop there, and I'll just acknowledge our sponsors and take questions if we have time.
Yes, we do have time for
We've
questions.
done a lot of work with heaviside functions and continuum problems. And we do use what's called continuation methods, like slowly approach an actual discrete heaviside function. So we have a lot of experience with that. And we found two things to be useful. One is this strategy of slowly approaching a real step function. The second is actually manipulating your optimization algorithm. So we use a very common optimizer called method of moving asymptotes, which the topology optimization community uses quite a bit. And move limits, everything is set up, not knowing that there's this really strict nonlinear function. And so if we get in there and adjust some of those move limits, we actually get much nicer performance, even using a constant, pretty close to discrete step function. So it's a little bit of a slowly increase it to approach it. That's one strategy. The other is to get inside the optimizer and really force it to take smaller steps. And because that, whenever you do a linear approximation for a gradient, right, it's only valid over a certain distance. And when you have these sharp things, that distance becomes very small, right? So actually putting that in the optimizer. But yeah, great point. And it didn't show up as much in these problems, probably because they're very simple, right? They're simple elastic problems, and these cost functions are not very complex. But yeah, good question.
Do we have other questions? I'm going to add to this a comment that you're asking a computer to find an optimal structure, and the computer is trying to trick you all the time. So if you pose your instructions wrong, you're going to get funny results.
Yeah.
Always.
Yeah, you should always go back and interrogate your results, right? Understand why it tried to design what it did, and verify that that's correct. Yep.
All right, if you have no questions, then thank you so much. I just wanted to add, if you feel like you can add anything to structural optimization, either through presenting next year's session or joining our committee, please come see me. Okay? Thank you.